Hi everybody, this is Greg Brady and this is on t-distributions and confidence interval. This is going to be kind of a long lesson and I'm at school, so you might hear an announcement or some background noise. Just disregard that. We'll try and get through this. But okay, so in practice the population standard deviation is unknown, so we then estimate the standard deviation from an SRS of size n from a population of interest. Okay, and we estimate the standard deviation by using the sample's standard deviation, which we can calculate in our calculator. Okay, the estimate of your sample standard deviation of your sample mean is that. Okay, and it is this formula right here. This is my sample standard deviation divided by square root of n. Doesn't that look familiar? Okay, it's the same formula except it's not the standard deviation. Okay, and it's called the standard error of the sample mean. All right. So one sample t statistic, not a z statistic, then becomes this, you guys. Doesn't that look familiar? The only thing different is the s. The s is our sample standard deviation. So everything's the same, you guys. Okay, and then n minus 1 is called degrees of freedom. All right, don't be too scared about that df thing. It's just a new term for, and it means we're in the t distribution, you guys. So we don't know the standard deviation for the population, so that would be a z statistic. We're in a t statistic, so we only know the sample standard deviation. Okay, characteristics of a t distribution. Now that's similar, you guys. I should have just typed in similar, but this is my squiggly line for similar. Very similar to a standard normal curve. There's one. Sorry. Varies a bit greater than that of a standard normal curve. It just varies a little bit more, flares out a little bit more, with more probability in the tails and less in the center of the standard normal curve. And the more your degrees of freedom increase, which means the bigger your samples are, the more that your t-distributions approach the standard normal curve. Okay, and it says, see this figure right here. Okay, so this solid line is the standard normal curve right here. Okay, and the bigger dotted line, the one that's a little bit lower, is when we had a degrees of freedom of 2. Well, that means your sample size was 3, because remember the degrees of freedom is n minus 1, so 3 minus 1. And this one right here, the smaller dotted one, look how close that baby is. That baby's really close to the standard normal curve, and that was when it was only 10 in the sample, degrees of freedom being 9, 10 minus 1. Okay, so it gets very close, you guys. All right, so using table C, so here's to get the table T. Okay, so everybody has table C now. And table C, I don't know why, but it always gives you the area to the right. And we've been doing the table A, which was the area to the left, but table C is the area to the right. So here's number one. What critical T value would you use for a T distribution with 18 degrees of freedom and having a probability of 0.9 to the left? Okay, well, since it's table C always wants the probability to the right, then 0.90 to the left is the same as 0.10 to the right. So look at the top, you guys. Well, I'm sorry, go down to your left-hand column to the DF of 18 and go across that top row to 10 and find out where they intersect. And you're going to use the t-score of 1.330. Alrighty? All right, so here's number two. You want to construct a 95% confidence interval for the mean of the population. So based on an SRS of size n equals 12. So what is t? Okay, remember your degrees of freedom is n minus 1. So you're going to go down to 11. Okay, and then down on the bottom column, down at the bottom of the page is your confidence interval. So go find your 95% and your degrees of freedom to be 11. And you should use the t-score 2.201. All right, so your t confidence interval is just like a z confidence interval, you guys, except the only difference is you're using the s right here instead of the standard deviation of the population. Okay, everything else is the same. Okay, and this is my standard error. This s over the square root of n is my standard error. All right. Also, if the standard deviation was known, then I'd use this formula. This is from the last chapter. See the difference? Only the standard deviation is from the population here, and this is from the sample standard deviation right there. Alrighty? Okay. So, and then where t is the upper 1 minus c critical values, because it's 1 minus the critical values for the t minus 1 distribution. I'll show you in just a second. Larger n values give more closer normal curves. All right, so auto pollution. Okay, so see example 11.2 on pages 622. You're going to need your calculator, you guys. Okay, so here, environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutant is hydrocarbons, monoxides, and nitrous oxides, so they do NOx. Table 11.1 gives the NOx levels in grams for a sample of light-duty engines in the sample. Okay, now look, it doesn't say it's a sample from the population, so we've got to write that. It does not say that. Okay, it's just a sample of light-duty engines, so we don't know if that came from the true population. Okay, now let's pause it right here, and you're going to enter all those numbers into list 1. Clear your list first, and then enter into list 1. When you come back, okay, then we're going to construct a 95% confidence interval. I'll show you by hand, and I'll show you on the calculator for the NOx emitted, okay? All right, so step 1, yes, we got to go through this procedure on this one. Okay, step 1, identify the population of interest and the parameter you want to draw your conclusion about. The population is all light-duty engines. We want to estimate the population mean, the mean of the amount of pollutants. Oops, I spelt that wrong, sorry. I'll get that in a second. Did I? Pollutants. No, I guess not. Emitted for all the engines. So, okay, step 2, choose the appropriate inference procedure. Verify the conditions for using the selection. Okay, so we don't know, since we don't know the the population standard deviation, that's what this is, sigma right here, we're going to use a one sample t procedure to construct a confidence interval. Because remember, back here, you guys, it said construct a 95% confidence interval. So we're going to use a t distribution for my confidence interval. Okay, and then the data comes from a sample of 46 engines from the population of all light-duty engines of this type. But we're not told that the sample is a simple random sample. So if it was not a random sample, then you're going to hesitate to draw conclusions. So you're going to proceed with caution. Okay. Also, the problem does not state that the population distribution of NOx is normal. It's just not stated there. Okay, so what you want to do is graph a stem plot, you guys. So you guys can do it, and you have to graph it, and you have to show that, and just show them that you know what you're talking about to see that this is normal. Now, besides this big number right here, it's pretty darn symmetrical. And on top of that, with the size being 46, my central limit theorem tells me that the sample means will be approximately normal. So we can go ahead and proceed, you guys. So step 3, if the conditions are met, carry out the inference procedure. There's my formula. Okay, when you plug those in, go to stat and then scroll over to calculate and do one variable statistics with list 1, and then you'll get those numbers right there. Okay, look, this is my sample standard deviation right there. Do you see those in your calculator? Do that. Pause it right now and do that. Okay, and then when you plug them in, since your DF column only goes from 40 to 50, you always round down, so it's going to give you a higher critical T. That's a wider confidence interval. So when I round down to 40, so scroll across at 40, your degrees of freedom at 40, okay, and a 95% confidence interval. So if you do that, 95 is down on the bottom, and at 40, and you get 2.01. Okay, so we're going to plug them all in, and then here we go. And I get that confidence interval right there. Okay, now let's try this with our calculator. Okay, go ahead and hit stat. Okay, I'm doing it with you right now. I'm going to hit stat and then scroll over to tests and then scroll down to mine's number 8, a t interval. And then you'll see it says, and then plug it in under data, and then you make sure you're pulling at list 1, and we're doing a confidence interval of 0.95. Okay, and then hit calculate, and it calculates for you a nice t interval. Mine's still thinking, it's still thinking, it's still thinking. Okay, I get 1.1848 to 1.4725. Okay, pretty darn close. Okay, so interpret your results in the context of this problem. We're 95% confident that the true level of NOx emitted by this type of light-duty engine is between 1.185 grams and 1.473 grams per mile. Okay. All right. Let's try one more. And this one I'll give it to you pretty much. You don't have to write as much down. Significance test for population mean when your standard deviation is unknown. So this is example 11.3. Okay. Cola makers test new recipes for loss of sweetness during storage. Trained testers rate the sweetness before and after storage. We kind of did this problem before. Here's the sweetness loss, sweetness storage minus sweetness after storage. Sweetness before storage minus sweetness after storage. So remember, if this positive 2 means it lost sweetness. This right here, negative 0.4, means it gained sweetness. Okay, so found that 10 tasters from a new cola recipe. So are these data good evidence that the cola lost sweetness? Okay, so we're going to go ahead and crank it out. So step 1, identify the populations. And so There it is, my HO, no difference, and my HA is greater than 0, means that it did lose sweetness when it's greater than 0. All right, and then step 2, choose the appropriate inference procedure and verify the conditions for using the selection. Okay, we do not know that the standard deviation of sweetness loss in the population of tasters, so we're going to use a one sample t-test. So now we must check the 2 requirements. We must be willing to treat the 10 tasters as an SRS from the population of tasters. If we want to draw any conclusions about the testers in general, the tasters all have the same training, so even though we don't actually have an SRS from the population of interest, we're willing to act as if we did. That is good stuff, you guys. Isn't that? Doesn't that make you feel all giggly? Okay, this is a matter of judgment. Okay, so perfect, beautiful. Okay, this assumption that the population distribution is normal cannot be effectively checked with only 10 observations. In parts, the researchers rely on experience with similar variables. They also look at data. We can construct a stem plot of the sweetness and loss. Here's a stem plot right there. Okay, and that distribution is somewhat left skewed, but there's no gaps or outliers, so there's no signs of non-normality behavior. So we're going to proceed with caution. Gold right there. Okay, so here we go. Plug all those numbers in. Okay, so and we get calculate the test statistics. Okay, and we just want to know it's greater, and so the sample mean was 1.02. So we do 1.02. We plug that in our calculator and got the sample mean minus 0 divided by my standard deviation, which we got from a one variable statistic. We got both these numbers right here from a one variable statistic, okay, divided by the square root of 10. It got me 2.70. All right, so find the p-value. The p-value for t equals 2.70 is the area to the right of 2.70 under the t distribution curve. And the degrees of freedom would be 9, 10 minus 1. Figure 11.4 shows the area. That's on the next slide. We can't find the exact value without a calculator or computer. I'll show you that in the next video. But we can pin p between two values. Okay, we're looking for 2.7. So look, if we go, can you find your degrees of freedom? Go to your degrees of freedom, column 9, and when you go down there, look for the ones that's 2.70 is somewhere in between these two guys. So that means the probability is somewhere in between 0.02 and 0.01, okay, which is less than 0.05. There's that figure right there. And so it's actually 0.0122 right there. So interpret your results, because the observation t lies between those two scores, the p-value lies between those. So here's the interpretation. A p-value this low gives quite strong evidence against the null hypotheses, and we reject HO and conclude that the cola has lost sweetness during storage. Yippee!